that off, okay? So hopefully you remember mass spectroscopy from topic 1, okay, and interpreting mass spectra. It's a very, very sensitive technique, and we can use it not to just identify particular elements, but it can also be used to identify compounds. And we only need samples, we need very, very small samples. Even a few milligrams is enough to identify compounds. Okay, and it's useful because if we've got an unknown material, the mass spectrum of that unknown material can be compared with a database of known compounds. There's a man using a really big looking mass spectrometer. We can make them far, far smaller than that these days. Okay, but for example, mass spectroscopy is important in forensic science. So, for example, it might be able to link a suspect to a weapon that has been fired. Leave that there for a sec. Okay, so I'm going to click that slide on. Been there way too long. Mass spectroscopy has also been really important in space as well, in space exploration. These mass spectrometers have been included on board several different space probes, whether they're actually in space or they've landed on a different planet or a different moon, okay, to explore what kind of compounds might be present there. Here we go. So in 2005, never quite known how to say that word, Huygens probe landed on the surface of Titan. Titan is the largest moon of Saturn. Here we go. During the descent, the mass spectrometer analysed the atmospheric composition at different heights as it went down towards the surface of Titan, and it found out that the atmosphere was mostly nitrogen and methane. It also found some argon-40. Yeah, sounds about right. Okay, which you wouldn't have completely known had you not done that at all. Scientists theorized that that was what the atmosphere would be, but they didn't know the exact composition at all. Okay, we don't need to necessarily know the ins and outs of the mass spectrometer, so I'm not going to dwell on this too much, but what you need to remember is that when we analyze a compound, the gaseous molecules get bombarded with electrons from, I like that, an electron gun. Yeah, and they knock out an electron from some of the molecules, creating what we would then call a molecular ion. Yeah, the molecular ion travels all the way around. If you follow the pointer, okay, this is where the electron gun is, just here. Okay, the ion gets whizzed around, accelerated through a magnetic field, and then detected at the end. Okay, so that at first thing that happens is that we create a molecular ion, just knock off one electron, and that will go round to the detector plate. Okay, and the peak with that highest mass to charge ratio, M to Z, is formed by that molecular ion. So the biggest peak, or the peak with the highest mass to charge ratio, and often it's the biggest peak, that value of M to Z is equal to the relative molecular mass of the compound. Okay, but as you know, in organic chemistry, there are many, many different compounds that can have the same molecular mass. They may be isomers of each other, they may just be different combinations of carbon, hydrogen, oxygen, nitrogen that have the same molecular mass. So I'll leave that there just for a second for you to digest. Okay, ready? Moving on. So there we go. So molecular ions and different peaks. So the peak at the highest mass to charge ratio, we kind of said this on the mass spectrum, is formed by the heaviest ion that passes through. Unless every single molecule of the original substance breaks up, this would correspond to the molecular ion of the sample substance. Okay? So that is the mass spectrum there of paracetamol. Okay, you can see the biggest peak with the highest molecular mass, or M to Z, is labelled there. That's the molecular ion peak made by the molecule that has just had one electron removed from it. Okay, we're going to come to that in just a sec. So, you'll notice as well that there is a tiny little peak just to the right of the molecular ion peak there. Okay. Probably don't want to be copying that whole spectrum out. That's going to be really irritating for you. Okay. We'll come back to that in just a second. And we talked about this back in topic 1. I know that we talked about this. High resolution mass spectroscopy. Yeah. Because if we've got a high-res mass spec, we can effectively calculate the molecular mass down to 4 decimal places. At that kind of accuracy, we can work out exactly what the empirical formula of the compound is. Okay, because all of these masses, so oxygen is 15.9994. Okay, it's not 16 at that level of accuracy. And so added to a hydrogen, even though you could make combinations that would add up to whole numbers that are simple to work out. Okay, when you do it to that kind of accuracy, there are only specific combinations it can be. And so you can work out the empirical formula from a high-res mass spectroscopy. There you go. And that's the difference, okay? So if you've just got whole number values, hexane and pentanal both have an MR of 86. But if you do it to 4 decimal places, hexane is 86.1106 and pentanal is 86.0739. Now that's a tiny difference, 0.04 thereabouts, okay? But it makes a big difference. There you go. So with a high enough resolution, it's possible to distinguish between what is hexane and what is pentanal. And you wouldn't be able to tell that normally. They're both colourless liquids. I think Mr. Barfoot just lost the plot. Okay, any questions so far? You're very quiet with me this morning. Everyone must be really happy. Why can't you look at me when I smile at you like that? All right. Oh, high resolution mass spec. Right. Let's do a little. We need the data. Good. You're going to need a calculator, folks. I'll get you the data in a second. Hopefully it just pops up there. There you go. Perfect. So what is the MZ, the mass to charge ratio of the molecular ion peak of propan-2-ol on a high resolution mass spectrometer? Oh. I got it. I know what it is. Oh, a few people have got it. You probably did it quicker than me. You probably had your hand up for the last minute. James, which one do you think it is?
The last one, 60.0581.
Okay, I think I agree with you. My calculator says I agree with you that it's the last one. Correct. Okay. What you hopefully did was, well, we know that M over Z is equal to the MR. You probably didn't even do that step. The empirical formula is just C3H8O, fair enough. Calculate the MR, add it all together. Okay, all of those. Next. Okay, put the data up again. What is butanoic acids? Oh, you're so much quicker than me. How did you do that? I think I made a mistake somewhere and had to go back again. Gabby, go on. 88.0530. Correct. Good. Okay. Oh. Now this is a bit more difficult. It has a molecular ion peak at 30.0474. What is the sample compound? I'd imagine that. Well, you can work it out. Nah. It is actually only a choice of two of them. Right, why is it not working properly? You got it. Why is that not? We need to restart that. Who's happy they got an answer? Bismuth. Ethane. Okay, it is ethane. Definitely. Which other one is very close to it though? Huh? Methanol. Yes, methanol. It's very close to it. But if you add them all up, you will find that it definitely is ethane. Correct. There you go. Last one then. What is the empirical formula of a compound that gives a molecular ion peak of 44.0011? Oh wow. So it could be three of them by the looks of that. Maybe, unless my math is gone. I think I know which one it is just by looking at the numbers, but I might be wrong. We'll see in a second. Yeah, he's right. Yeah, good. What you got, peoples? Go on, Leanne, you want to say? N2O. I think I agree with you. Anyone disagree? None? What's up, Gabby?
I didn't check all of them.
You didn't check all of them, but you thought it was N2O.
Yeah.
It's only going to be one of them, to be fair. Okay, so the first one could be 44. So it's possibly that. This one, what's that? That's 24, 28, and 16. That's 44 as well. But 24, 31, this one's 45, so it couldn't be that one. But it could be any of those three. Well done, people. You can work it out. High-res mass spec. Well done. That's good. Now, do we have on here n+1? No, we don't. Okay. So I'm going to go back to this for a second. Right. So some of you noticed on this one, and you're very good to notice it, you've got a peak here, just beyond the molecular ion peak, but it's much, much smaller than the molecular ion peak. Okay? In fact, normally it'd be even smaller than that, to be fair. We call this the M+1 peak. It is at a mass of 1 over the mass of the normal formula mass of the molecule. Okay? Which seems really, really odd, doesn't it? How can you get an ion that is 1 heavier than it should be? I wonder if any of you can come up with an idea first. Where did this M+1 peak possibly come from? Go on.
I don't know from where, but I think that's...
I see your idea. So adding a proton or a neutron, I guess that would be pretty difficult because you're only firing electrons at the sample in the first place. Okay. But what do we know about atoms? We know something very important about them. Could be an isotope. Exactly, Ziad. Correct answer. Okay. It's all about isotopes. Let's see if we can come back over here and see this that way. Good. So the molecular ion peak, the M+1 peak. So it's a small peak. One beyond one beyond the molecular ion peak, and it's caused by, exactly as he had told us, okay, it's caused by atoms of carbon-13. And why is that important? Well, normally about 1% of carbon atoms are carbon-13. Okay? So actually, if we do a mass spectrum for a atom that only contains, or a molecule that only contains 1 carbon, then the M+1 peak is tiny, you probably wouldn't even see it. But the more carbons that we have, the more likely it is that one of them will be replaced by a carbon-13. And so the longer the chain gets, the bigger this M+1 peak becomes. Okay? Statistically, it's very, very unlikely that you get an M+2. There is a tiny, tiny one here. But again, paracetamol has don't know exactly how many carbon atoms, somewhere around about 10. So you should find that this will be about a tenth of the size of this one. And then this one would be like another tenth again. Okay? So that would be like 1%, that M+2. But the M+1 is important, okay? You will see it. And the longer the carbon chain gets, the more likely you are to actually see an M+1 peak. Okay? So it's caused by atoms of C13. Approximately 1% of carbon atoms are carbon-13. So a long chain. There you go. That'd probably be the maximum. We don't often really see even chains up to 10, but if it was around about 10 carbons, then the n+1 peak would be about 10% the size. 1% for every carbon atom that you have in the chain. The mathematicians in the room will be able to work out the probabilities, I'm sure. That's what it is all about. It's all about probability. Okay. Good. Any questions on n+1 peaks? No. Let's bring this back around in that case. Good. So crack on. Have we done that? Oh yeah. Okay, now, when it comes to organic compounds, you saw this in the spectrum of paracetamol. It had a lot of peaks that were much lower than the molecular ion. Okay, this is what we call fragmentation. When we fire electrons at our organic compounds, taking an electron off tends to make them a bit unstable. Okay, we know ourselves, don't we, that even when we were looking at mechanisms, some cations, carbocations, were more stable than others. Yeah? And so when we fire an electron at a compound, it might start to break apart and we can end up with different fragments. This is where mass spectroscopy really starts to become powerful for us. Okay, we can almost use it to work out the structure of compounds. And these days, as we've got a database of virtually every compound that we know, we can just get a computer to compare it back and see exactly what we've got. So I'll play this and you can see. There you go. So that's the mass spectrum of compound with the empirical formula C3H6O. And you could confirm that if you did a high-res mass spec on it, you could confirm exactly what it was, okay? What we see in there is, well, someone tell me, where is the molecular ion peak? Approximately what is its mass, the molecular ion peak? The molecular ion peak. Not quite. Let's, because you said 29, 28. What do you say, Ziad? 57, yeah, something around about that. Still, the molecular ion peak needs to be up here. Needs to be one of the high, like, with the highest mass to charge. Okay, that probably is 58 to be fair, but it's a bit of a strange scale they're showing. To be fair, I don't know why you would split 10 up into 4 different parts when it's not even a multiple of 4. Anyway, so that's our molecular ion peak there at 58, and that probably does make sense. We got 36 for the carbons, plus 6 is 42, and 16, yeah, 58. Okay, so that's the molecular ion peak there. The rest of these are from fragments. Okay, if this one is just one lower, what might have happened to it if it's just one lower? What might have happened to that molecule? What might have been removed from it if it broke? Or a different question, what has a mass of just one? Huh? Hydrogen, exactly, yeah. Okay, so it may have just been a hydrogen broke off. And you've got all of the molecule except hydrogen. Yeah? This will be C3H5O. The other fragments we will have a think about as well. Okay? So, for instance, here we go. High-res mass spectroscopy cannot distinguish between propanal and propanone. They have exactly the same empirical formula, molecular formula. They're just structural isomers of each other. And there's no way, because they've got the same number of atoms, there's no way that there's any difference between those. But a mass spectrum can tell the difference. Okay, and it will tell the difference in terms of how it breaks up. Yeah? So there's propanal. It's showing their molecular ions. It's showing that they've got a plus charge. It's also got a little dot to say that one of the electrons is unpaired now. Okay? Like a free radical. The little dot is really not important. Okay. So the molecular ion M+ may split into fragments, into pieces in a process, yes, that would make sense, called fragmentation. So it's labelled up all of those fragment ion peaks. So there's 4 of them there, and then one right next to the molecular ion. Don't need to tell you much more than that. But if we have a think about the possibilities, okay, of breaking, then propanal can break up into that. It can break up into a CH3. It could break the other bond, and then you've got CH2 and a COH together. Okay, and they have different masses. You've got MZ15 for the CH3 part, and a 43 for the other part. Yeah? So all you've got to do is really add the fragments together, or add the masses of all the atoms in the fragments together. You could also, from propanal, make fragments like that, both of which have a mass of 29. Yeah, it's almost like breaking the molecule in half. So they could all come from propanal. So you've got fragments at 15, 29, 43. Yeah? Happy with that so far? Okay, and there you go. It's possible that we've got a 57 and a 1 as well. Okay? And we've kind of seen that, I think. Normally when we look at fragmentation, it is a bit more complicated than that, but we just look at breaking one bond to make a fragment. Yeah? Otherwise you could carry on all day breaking bonds, yeah? But thank you for the question. Where's my pointer? There it is. So, propanone, though, a bit different. We could still make a fraction a bit like that, CH3 and the CH3 and a CO this time. It's a slightly different fragment than before, but it still has the same mass, 15 and a 43. Another option, there's not much. In fact, there is not much at all. Okay. We couldn't make from propanone, and I think it jumps a bit too much here, but this fragment here could only come from propanal. It could not come from propanone, because propanone would have to have a carbon bonded to an oxygen here. Okay, so that fragment just confirmed to us that this spectrum must have come from propanal. Yeah? Which is pretty cool. I know everything is pretty cool in my world, but... So, let's see. We've got several that we can interpret right here. Let's pick one. Aha. Right. Looking at that fragment there, MZ equals 29. There's a nice question for you as well. Which fragment ion does that peak correspond to? Put your hand up when you got an answer. Ziad, I can't believe you're the only one who's actually got your calculator out and is tapping things away. Go on, tell me. CH3, CH2. I think you're correct. It's the only one that adds up to 29. Good. Okay. Which? So we've identified it. It's a CH3, CH2 plus. For M over Z equals 31. What is that? I'm not coming back to you, Ziad. I'm going to let someone else work it out. January, are you tapping away on your calculator? No. Oh, you got it anyway. Okay, CH2OH. Yeah? You did it in your head, didn't you? There's me picking on you. I am sorry. So you think it's CH2OH? You are correct. Okay, good. So now we've identified two fragments. There's a fragment there at 43. James?
The last one, CH3, CH2, CH2.
Okay, CH3, CH2, CH2 plus. Correct. Now, the molecular ion peak was at 60. It can be, I believe, possibly any one of those compounds. Not sure they all have the same mass, but when you look at the fragments, there's only a certain order that you could put the fragments together that could possibly make a molecule with a mass of 60. Okay. James? The first one. Yeah, propan 1-ol. Okay. It has to be. Correct. Okay, and you can really just work it out from here. Okay. If you know that your molecular ion peak has a mass of 60, okay, well these two were 29 and 31. Add them together and you'll make the compound. Okay. And this as well could only possibly come from propanol out of the options that you had, the options that have now gone off the screen. Okay, that's cool. Try another one, try a bit quicker this time. That was that one, I think. Yeah, try that one. Okay, that's easy, MZ15, that's a really common fragment. Leanne? CH3, exactly. We very often see CH3 fragments. Next, 31. Again, we had 31 before. Come on, who have I not spoken to yet? Maria? CH2OH. Is that 12, 16, 28? Correct, good. I wasn't disbelieving you. So that's CH2OH, okay. We've got an MZ equals 45 up here. Very close to our molecular ion. What is it? Ziad? The last one, CH3, CH2O plus. Correct. Okay, that's our molecular ion peak. Okay, it doesn't have to necessarily be the biggest peak, but it'll be the most significant at the highest M over Z. Okay, just what this tells us is this molecule is very likely to break up. It's very likely to fragment. Okay? So, identity of the compound, you can almost tell from this one, it's only one below it. Should be quite straightforward from this. Jemima, what do you think? The last one? Huh? The last one or maybe the first one? The first one. You're correct. Okay? All you had to do really was to just add a hydrogen back onto this. Okay? Perfect. Okay? How do I get back out of that? There we go. Last one. So, you know this already. Pranesh, you've not really spoken to me at all today. Which fragment is this? Good. Okay. 29, we've done 29 as well. You'll start to notice that they repeat themselves quite a lot.
Is there a reason why the fragmentation was used? Or is it like, is there something about the characteristics of why these like fragmentations occur again? Like, because we always seem to be in the same distance of them.
Because fundamentally their structures are very similar. Like CH3 is, you know, almost on every compound that you could make is a CH3 group at the end, yeah? 29, we did this one before. Gabby? The middle one. There you go, yeah, CH3, CH2. Oh, a nice big one there, and we've done that as well before. 43. Julia? Almost there. The last one. Correct. Okay, so we've got to work out from the fragments and now the molecular ion. So the molecular ion has a peak at 58. You know the fragments. There's actually only one it could be from those options. Even just looking at the fragments without using your calculator. Why is it you whispered it? Go on, tell me if you whisper it. The first one. Okay, yes. I think you're right. It's the first one. There you go. Awesome. We can do mass spectra and fragmentation. Oh. There's an interesting one that didn't actually come up. What do we think about these true and false statements? A mass spectrometer can be used to determine the presence of an illegal drug mixed with flour. I don't know why if you had an illegal drug you mix it with flour, by the way. It sounds like an odd idea, but there you go. What do you reckon? Trues or falses? True. True? A couple of people saying true. Let's see. Yes, I thought it was true as well. The M+ peak in the spectrum of methane, so that's the molecular ion peak, would have an MZ value of 15. A lot of nodding going on. You're saying true? You're saying false, Liad? Gabby's almost saying false. It is false. It would be 16. CH4. M+ peaks are always the peak with the highest M to Z value on the spectrum. Nee? Yeah. The x-axis. They always are? A lot of other people saying false. That's really harsh. Not if you include the n+1 peak. Probably because they're not really talking about n+1 in this PowerPoint. But you're right. You are right to say false. All of you. I would have said false there because you've got the n+1 peak. Bad PowerPoint. High-res mass spectrometry cannot differentiate between structural isomers using the n+ peak alone. So could you just differentiate between propanal and propanone with a high-res without any fragmentation? No? Yes? It is true. You can't differentiate. Good. A compound can be identified by comparing its mass spectrum with the spectra of known compounds. A few little noddy heads. Yeah? It is true. Okay? So actually we've got quite a lot of learning in there today. I'm quite impressed. We're not going to do that bit, but that's coming up soon enough. Infrared spectroscopy. Okay? Which is a bit crazy, but very interesting as well. Okay? Analytical techniques are extremely useful for chemists. Extremely useful to identify things, okay? Not just like, putting magnesium in something and seeing it fizz. You can't really completely tell what something is from that, okay? But mass spectra, infrared spectra, then when we go on next year, we'll look at, I'm just doing this for year 13 now, proper chromatography, real chromatography, not with paper. And the last bit in year 13 is NMR spectroscopy, which is mad. Yeah, it's that little poster up there. Yeah, exactly. A guide to NMR chemical shift. Exactly. That's the one right there. But that's like this time next year. Something to look forward to. Not that you don't look forward to every single lesson in here, obviously. All right, folks, I think we're good for today.